it's very cool to work in problems that you cannot resolve by yourself. You need tools and you need to... It's a complete different way to resolve things. You need to learn very separate things on how to scale things up, but then the result is amazing because you can really see that it's a complete game changer. And also because doing science is fun. I mean, you get to play with things every day and you get to discover, and I don't know, I don't imagine myself doing something else than science. I think it's a very, very fun way to live. I'm Xulia Docampo, and I'm a established researcher here at the CASE department within the Computational Fluid Dynamics group led by Uriol. I think Barcelona is my home in some sense, and being at the supercomputing center like this is a great opportunity for research and in general, very good environment. I work developing tools for adaptive mesh refinement, which is basically how you represent the geometry in the computer. And depending on the type of problems that you have, you can resolve more in the geometry in some regions and leave other regions unresolved. And basically what I developed is algorithms that actually target that. Where there is information, you want to have a high resolution, and when there's no information, you just want to have a less intense mesh. HPC enables to resolve a problem that is actually giving you the information that you need. So if you want to really resolve a high fidelity problem that can be related to turbulence or can be related to what's happening very near the ground, you really need to have high performance tools. This is the only way to detect where things can happen, because if you just have a small sample, then you're going to solve the problem, but you're not going to be able to see the phenomena. So in order to see the phenomena, you really need to go into detail. And the only way to go into detail and actually resolve is having supercomputing tools. Otherwise, there is not enough memory in your computer to do it. For example, what I do is I basically have a geometry and I have to resolve the geometry. And you can do it in two ways. You can have the full geometry in your computer and do it, or you can have your geometry split into many processors or many CPUs, and each CPU does their own work, and then they come back together and they bring the information together. So basically, if you are able to subdivide the geometry that you have, in this case the mesh, then you can compute the same thing in several spots, and then you are doing the task 10 times faster. One thing that I think it will definitely have an impact is a project that we're doing with my colleague Abel and our PhD student Alice, that is related to wind farms. And basically what we're doing is we're actually developing meshes that are able to resolve the layer between the ground and what happens very near the ground, because that's where all the activity related to the air happens, and that's where the wake from the turbine is going to have an impact in the rest of the turbines. And what we're doing is we're developing an adaptive tool that actually only resolves where it needs to resolve, and then what it does is that it captures very well the layer. It's called the atmospheric layer, which is what happens very near the ground. This is very well captured, but it also removes a lot of the information outside, so it becomes tractable. So in the context of wind energy, this is going to be a very different way to compute, because before they use something that is very intense in terms of computations, and we are able to do it way faster. So we think that this is going to really be a difference.